Whole numbers. In this module, you will learn about predecessor and successor, whole numbers, representation of whole number on the number line, properties of whole numbers, and patterns in whole numbers. We have already learnt about counting things in numbers, such as 1, 2, 3, 4. These numbers are called as natural numbers. We can write it as a set of natural numbers, denoted as capital N, where n is equal to 1, 2, 3, 4, to infinite numbers. If we see here while adding 1 to any natural number, we get the next natural number. For example, adding 1 to 3, we get 4. In the same way, adding 1 to 15, we get 16. Similarly, if we subtract 1 from any natural number, we get a natural number. For example, subtracting 1 from 7, we get 6. In the same way, subtracting 1 from 23, we get 22. So we can say here that the next number of any natural number is called its successor, and the number just before a number is called its predecessor. For example, the successor of 10 is 11, and the predecessor of 10 is 9. What if we subtract 1 from 1? Do we get a natural number? As we see, the number 1 has no predecessor in the set of natural numbers. Therefore, the natural number along with 0 from the set of natural numbers is given a new set name as whole numbers. The whole numbers are represented as W, where W is equal to set of 0, 1, 2, and so on. Let us represent whole numbers on a number line. Draw a line. Mark a point at start of line. Label it 0. Now, mark another point at some distance from 0 and label it as 1. In same way, mark points 2, 3, 4, respectively, at equal distance from 1. Here the distance between any two consecutive points is called unit distance. Now what we can say about the distance between 3 and 5? It is 2 units. Can you say the distance between 7 and 12? Yes, it's 5 units. Here, arrow on the right side represents that the number is continuing till infinite. The number lying on the right side of any number is its successor. So we can say that all the numbers which lie on the right of a number are greater than that number. For example, what is the position of these numbers on the number line? Addition of whole numbers can be represented on a number line. Let's see the addition of 3 and 6. Start from 3. We need to add 6. So we make 6 jumps to the right and we reach to the number 9. So the sum of 3 plus 6 is equal to 9. Whenever we add two numbers, we move on the number line towards right, starting from any of them. Subtraction of two whole numbers can also be done on a number line. Let's see 8 minus 3. Start from 8. Since 3 is to be subtracted, move 3 jumps towards the left. We reach to number 5. So 8 minus 3 is equal to 5. Thus, while subtraction we move towards left on a number line. Let us now see multiplication of whole number on a number line. Let us find out 4 multiplied by 3. Now 4 multiplied by 3 means taking 4 steps 3 times. So starting from 0, taking 3 jumps towards right, each of 4 steps. We reach to 12. So 4 multiplied by 3 are 12. Take any two whole numbers and add them. We observe that the sum of any two whole numbers is always a whole number. So the collection of whole numbers is closed under addition. This property is known as the closure property of addition for whole numbers. Let us check for multiplication. We see that product of any two whole numbers is found to be a whole number too. Hence we can say collection of whole numbers is also closed under multiplication. If we check for subtraction and division, the closure property does not hold. Division by a number means repeatedly subtracting a number from the dividend until we get 0. Example, 10 divided by 5. Here we get answer 2. What if we divide 5 by 0? Let's see. After every subtraction we get 5. Will ever 0 come? No. Therefore, any number divided by 0 is not defined. Have you observed this following addition? In both cases, the sum remains the same, though the order of a pair of whole number is changed. This is true for all whole numbers. So we say this as an addition is commutative for whole numbers. Now, observe this pattern. Here also, in both cases, the product remains the same for multiplication of all the whole numbers. Hence, we can say multiplication is commutative for whole numbers. If we check for subtraction and division, the commutative property does not hold. If we observe the following, we see that if we add 4 and 3 first, then add 6 to their sum, and if we add 3 and 6 first, and then 4 to their sum, we get the same result. This property is called associative property for addition of whole numbers. Try it with some other whole numbers as well. Does this property also hold for multiplication? Let's check. If we multiply 6 and 5 first, and then multiply 10 to their product, we get the same result. If we multiply 5 and 10 first, and then multiply 6 to their product. Hence, this is called the associative property for the multiplication of whole numbers. If we check for subtraction and division, the associative property does not hold. Take a chocolate bar of 4 into 7 piece. Now cut it in 2 pieces, 4 into 4 and 4 into 3. Here we see that 4 into 7 equals to 4 into 4 plus 4 into 3, that is equals 16 plus 12 equals to 28. Also, since 7 equals 4 plus 3, we have 4 into 7 equals to 4 into 4 plus 3. Therefore, we can say 4 into 7 equals to 4 into 4 plus 4 into 3. This is known as the distributive property of multiplication over addition. When we add any two whole numbers, we get a new whole number, right? But what if we add 0 to any whole number? Do we get a new number? Let's observe the following table. We see adding any whole number to 0. The result is the same number. This property is called identity. Therefore, 0 is called as the additive identity for whole numbers. Similarly, observe the following table. We see here when we multiply a whole number by 1, the product will be the same whole number. Therefore, 1 is called the multiplicative identity for whole numbers. Let's make patterns by arranging the numbers in elementary shapes made up of dots. The shape we would make are a line, a rectangle, a square, and a triangle. Every number should be arranged in one of these shapes. No other irregular is allowed. Every number can be arranged in a line. Some numbers can also be shown as rectangles. Some numbers like 4 and 9 can also be arranged as square. Here, 4 equals to 2 multiplied by 2. This is a perfect square. And 9 equals to 3 multiplied by 3. This is also a perfect square. Some numbers can also be arranged as triangles. The arrangement in triangles would have its two sides equal. The numbers of dots from bottom row will decrease till 1 at the top. Observe the table and complete it on your own. Patterns with numbers are not only interesting, but are useful especially for mental calculations. See the following examples. Let us summarize all that we have learnt in this module on the whole numbers.